that we have at the moment now is that we have Euler's method, and the errors, the global errors, which are the ones we really care about, like what's the difference, essentially, what's the biggest, essentially, like the difference at the end, it's kind of a maximum, it's essentially kind of like the maximum difference essentially between them is order h. And so if we need to decrease the error by a factor of 10, we need to decrease the step size by a factor of 10, and that means 10 times more steps. And that becomes a difficulty with the computer, especially with the rounding error in the computer. So what we want to do is we want to kind of get something more accurate, that we don't have to have 10 times as many calculations to improve or decrease the errors by a factor of 10. So the first thing we could do is, if we look back at what we did, I think was it in the first week, we could move from, instead of using tangent lines, we could use tangent parabolas. So say what I'm saying here is, suppose here's your curve and you've got a tangent line. Go away. Sorry about that. And your tangent line, that's supposed to be, why can't I draw? Hey, instead of the tangent line, maybe use the tangent parabola, which can allow some amount of curve. Okay, now what is the tangent parabola? It's the parabola that looks most like, just like tangent line, it's the parabola that looks most like the curve at the point. So it's going to have same second derivative, same first. So basically a line is the same first derivative. A parabola is going to have the same second derivative. So given a first order differential equation, we're going to have to be able to find the second derivative, but that isn't too difficult. What am I doing? Because we have implicit differentiation, which I'm sure you learned about last year. So what you can do is, if you differentiate both sides of the differential equation, so here you'll get the second derivative. Now this is some formula in x and y, and if you differentiate it implicitly, you'll end up with some other formula which I'll call g. You'll have x's, you'll have y's, and when you differentiate implicitly, you'll have dy dx's. But the thing is, from the ODE, you have dy dx in terms of x and y. So really, you can get the second derivative in terms of x and y by substituting in for dy dx in terms of x and y. That might be a bit confusing. We'll see an example in a moment. So the first derivative here, in fact, is in terms of x and y. So in fact, we can find the second derivative just in terms of x and y. We got to be careful. The derivative of y respect to x, just dy dx, and anything like product rules apply, quotient rules apply. And if you have a function of y, it must be differentiated as a chain rule. So for example, if you have some function of y, now actually when I teach this, when I do teach implicit differentiation, like if you go back, I'm sure they would have done the theory with you. So you've something in terms of x and y. It's hard to do the theory here, but the idea is that the y really is a function of x. So really what you're looking at is y is a function of x. Like when you write down a first order differential equation, the x and the y aren't independent. Really the y implicitly depends on x. In other words, for each value of x, there's only one value of y. And so if you're differentiating a function of y, what I recommend is that you actually think of the y as y of x. And that makes it a little bit easier to see the chain rules and stuff. I'll do an example, I think, on the next page. Because if you just have what, like if you're just differentiating y squared, there might be a temptation to do 2y, which is wrong. But if you had y of x all squared, you'll see the outside function is the square and the inside function of the y of x, and you might be reminded to do the chain rule. So the chain rule says you differentiate the outside function, you evaluate at the inside function. Now I only write the y of x once, times the derivative of what's inside, and the derivative of y is dy dx. Now if you do that with, say, just x squared, you can, well, you don't say x a function of x, but if you do the chain rule with x squared, you get 2x and then times the derivative, the inside there would be x, the derivative of x is just 1. So this is to avoid saying that the derivative of y squared with respect to x is 2y. So hopefully we'll see a good example on the next page. Not really. I'll do just a little example up the top. So suppose you have big F of xy is equal to, and this is dy dx, remember, say x squared plus y squared for argument's sake. Actually, I'm going to put in a note there to make this a harder example. So so what I'm saying is, in my class, we rewrite the y as y of x. And then it's a bit easier to see the chain rule, and you're less likely to write down the derivative of y squared is 2y. So remember, this is just dy dx. So if I differentiate this, I get the second derivative, because big F is the first derivative. The derivative of x squared is fine, that's 2x. And now I use the chain rule for the derivative of y of x all squared. I differentiate the outside. The outside function is x squared. Derivative of x squared is 2x. The chain rule says evaluate at the inside. The inside, now I only write the y of x once, is y. And then the chain rule says multiply by the derivative of what's inside, and the derivative of y of x is dy dx. And of course, in this particular example, dy dx is equal to x squared plus y squared. And I think we'll see that in an example in this lecture as well, I think. Okay, so here we go. Here's an assessment question. The second derivative is required to implement the three-term Taylor method. So we'll learn about that in a second. Use implicit differentiation to find the second derivative if dy dx is x squared minus 2y of x. So we differentiate both sides with respect to x. So if you differentiate the first derivative, you get the second derivative. Remember, in these videos, pause me and rewind me. Equal to the derivative of x squared is 2x minus fix the constant 2. Now, what is the derivative of y of x? Well, the derivative of y of x is dy dx. And now what we do is, well, what's dy dx? Well, we have dy dx in terms of x and y. So here we see the second derivative in terms of x, y, and dy dx. And there's no y there, but in general there could be. So in terms of x, y, and dy dx, and then but you will have dy dx in terms of x and y. So that's what I meant down here. You have the second derivative in terms of x, y, dy dx, but you can put dy dx in terms of x and y. That's what I meant. I just realized that I've no kind of scroller. I can be talking and pointing to something, and it's no good. So apologies about that. So this is equal to 2x minus twice, and what's dy dx? X squared minus 2y, and we can multiply that out if we want. We get 2x minus 2x squared plus 4x. So if we wanted to do a tangent parabola and we wanted to find something out about the second derivative at the point, we can do it. Now what this actually implies is that, so we said if you have a differential equation with an initial condition, it gives you two pieces of information. It gives you the slope and it gives you the point. Now what this actually implies, and I didn't think about it before, is that you can actually calculate the second derivative. And that means in theory you can calculate the third derivative, the fourth derivative, the fifth derivative, the sixth derivative, etc. And that implies that you can find the Taylor series of the function if it's analytic. Now it's just that there mightn't be a nice pattern to it. So theoretically, if you keep differentiating and use the Taylor method, you can approximate the function like this, and you won't even need step sizes. Because what you'll do is just, if you take enough terms, as long as you don't get too far away from x0, it's going to be accurate. I suppose, as I said, the issue is that the issue is going to be you'll have to differentiate loads, and then there's a thing where the solution might only be analytic close to x0, which is a technical difficulty. So remember, now we're in the market for improving the Euler method. So let's go for the three-term Taylor method. So the three-term Taylor method is a more accurate method of approximating the solution. It uses parabolas, so you get a bit of curve going on rather than lines. So if we have an analytic solution, this is what I was kind of mentioning, then the y of x is equal to all this, certainly close to x. So this, if it's analytic, there'll be some region where this is accurate for x close to x0. Now you don't have to worry about checking are your solutions analytic or anything like that. So, that's written there. For points close to x0, we have that the true solution, the exact solution, is equal to an infinite sum. Now, I captured the infinite sum here by saying that there's loads of terms that are multiples of x minus x0 to the power of 4. Okay. Now, the first term is just your previous point as such. You've got slope. Basically, the first two terms here is called the tangent line. And if you take the first three terms, you get the tangent parabola. Okay. When we're particularly close to x0, so what we're thinking here is when we have an x1, that we're just a step size away. So particularly close to x0, so that means so x minus x0 less than the step size. That's all that means. Now it says in particular less than 1. Now that is relatively important, but not strictly. Then the higher powers, so these things, so if these are h's and say h is 0.1, this will be a multiple of 0.1 to the 4. That's just a multiple of 0.0001. Now that multiple of 0.0001 could be big, but in general we'll be hoping it isn't. So what we're going to do is just take the first three terms as an approximation. And this is the tangent parabola on the right hand side. So this here is the tangent parabola. And these are the three terms that you get this thing, the three-term Taylor method. And so what you get is that the Euler method is two-term Taylor. So usually what we do is we find a solution at multiples of the step size. So we end up with using our kind of stuff we did before. So if I'm looking at x1, y of x1, the exact solution at x1 is approximately what we call y1 plus, now I'm going to write, sorry, there's no plus there. So the y1 is this three terms in the yellow, which is equal to y of x0, which is y0, the starting value of y. Now x1 minus, if we're interested in this at x equal to x1, and in that case, this would be x1 minus x0, which is h. And I'm going to write this the other way around, plus step size times, now y dashed of x0, you're thinking is previous slope. So I'm going to write y dash 0, slope for the dashed 0 previous to 1, plus, now similar story, the x minus x0 squared is h squared. You see the divided by 2, take that, and then the y double dashed at x0 is at the previous point, so I have the y double dash second derivative 0 at the previous point. So we can tell the value of y dash is 0 from the differential equation. Do we know what this y double dash of x0? Yeah, well what we can do is we can do implicit differentiation like we've been doing to find the second derivative, substitute in x0 and y0, and off you go. So you end up with this thing down here that I've written slightly differently above. So like Euler's method, you can keep going. And so, yeah, so I should probably swap these the way I regularly write it. So you can get an iterative method, you can keep going different points, the notation is the same. So basically what is it? The next y value is equal to the previous y value plus step size times previous slope plus step size squared over 2 times previous second derivative. And the difference between them is this bit. So that's the difference between the three-term Taylor method and the Euler method, and that gives you a good bit of extra accuracy. So if we did the analysis that we did before, the tricky analysis from last week, the local errors are order h cubed and the global error is h squared. So that's good because say with Euler method, let's write this down. So Euler method, say you've got the global error. Now you don't know what the global error is, but just say for argument's sake it's 0.1. And suppose you want to get the global error down to 0.001. So you want to decrease it by a factor of 100 because the global error is of order h. To do that, you'll have to go from h to h over 100. So you're dividing the step size by 100. That means you've got 100 times more calculations. So the number of calculations goes to 100 times n, which is bad. Now for the three-term Taylor, for the same problem, if you want to get the error down, so we're trying to get the error down. So we're trying to get the global error from 0.1 to 0.001. Improve it by a factor of 100. Now here, the error is of order h squared. So maybe if I say that the original error to 0.1, it's equal to 0.1 h squared. So if I want to get that down to 0.1 h squared divided by 100, I don't have to divide the step size by 100. I only have to divide it by 10. So h1 equal to the original step size divided by 10 will do the job. And that means that the number of calculations only is multiplied by 10. So you get to get the same accuracy with the increase in accuracy of the three-term Taylor, you only have to multiply so to get basically 100 times better, 10 times more calculations. So it's way better. Now the problem with the three-term Taylor method is it involves more mathematics, the implicit differentiation, and that can get worse again if the thing is hard to differentiate or whatever. Because we can go to a 4-term Taylor and a 5-term Taylor, but the maths is just getting kind of a bit nasty. So that's something we're going to come back to, because it's not ideal. If we could maybe get the accuracy and keep things easy somehow. We'll see that a bit later. Okay, let's do an example. So now again, the differentiation isn't, I could have made the implicit differentiation a bit more complicated. Okay, so use the three-term Taylor method with a step size of 0.1 to estimate this. So we need to use this formula here now. I probably should do those the other way around. It makes no difference, they're just numbers. Now we have the derivative, we need to get the second derivative. So to get the second derivative, I differentiate the first derivative. So the second derivative, the y dash dashed, is the derivative of the first derivative. And the first derivative is up here, it's x plus y. So it's not too hard to differentiate. I differentiate term by term. So the derivative of x is 1, and the derivative of y is dy dx. And now what I do is, so I've got the derivative in terms of x and y and dy dx. Well, strictly speaking, just dy dx, but I know dy dx in terms of x and y. So I replace dy dx, substitute dy dx equal to x plus y. So the second derivative is 1 plus x plus y. Okay, now we'll probably, to help you here, we'll have a little table. We'll fit it over here, I think. So what's going on here is we've x and we've y, and we're at x equal to 0, and we're trying to find out what's going on at x equal to 0.2. We're going to go in jumps of 0.1. Hopefully some of this will make a bit more sense when you are after doing labs. So what do we have? We have at x equal to 0, y equal to 1, and we're interested in finding out what's happening in 0.2. Okay, so let us go. So go to the black bar. So the y value at the next point, which is x equal to 0.1, is approximated by what we're calling y1, which is equal to, in the three-term Taylor, the previous y value. Now the previous y value we can see in the table is 1, plus the step size, which is 0.1, times the previous slope. Now the slope is x plus y, So we want to calculate x plus y at the previous point. So the previous x plus y, look at the table, is 0 plus 1. Plus, we'll go for step size squared over 2, which I'll write as step 0.1 squared over 2. Then it's a little messy the way I've written it. Times the second derivative at the previous point. So the second derivative is 1 plus x plus y, which is 1. Previous x is 0. Previous y is 1. And we'll bang that into the calculator there and see what we get. 1 plus 0.1 plus 0.1 squared over 2 times the thing in that second bracket is 2. And I get 1.11. So that's our approximation to the y value at x equals 0.1. Now we go again, because we're trying to find out what's happening at, approximate anyway, what's happening at 0.2. So the y value at 0.2 is approximated by what we call y2, which is equal to the previous y value, which is 1.11, plus the step size, which is 0.1. The previous slope, now the slope we get from the yellow thing up the top is x plus y, which at the previous point is 0.1 plus 1.11. That's the previous x plus y, plus the step size squared over 2 times the previous second derivative. And the second derivative is 1 plus x plus y. 1 plus previous x is 0.1 plus previous y is 1.11. Okay, and we'll bang that into the calculator and see what comes out. So I get 1.11 plus 0.1 times 0.1 plus 1.11 plus 0.1 squared divided by 2 times 1 plus 0.1 plus 1.11. And what comes out is 1.24205. Now I'll only take that to 3 significant figures there. Okay. Now, of course, the thing is, if I was to calculate what was going on at 0.3, and if I use 1.24 rather than 1.24205, I'm adding to the error because I've got the truncation error, the order h squared local errors, and I'm adding to that by doing rounding error. So you want to be careful. And you have to realize computer always has some rounding error. So let's see, verify that this function satisfies the initial value problem. So what we want to do is just check that the derivative of this function here is equal to x plus this function, and at 0 it's equal to 1. So you can show it satisfies the differential equation, but then the initial value is also the initial value. So let's calculate dy dx, and I think we'll probably calculate x plus y separately. So dy dx here equal to, so the derivative of 2 e to the x, I probably fix the 2, and the derivative e to the x is e to the x. The derivative minus 1 is 0, and the derivative minus x is minus 1. Okay, we'll leave that there a second. And now let's calculate x plus y of x. This is equal to x plus y of x now is, just taking it from the question, 2 e to the x minus 1 minus x. And if you notice, the x minus x is 0, so you get 2 e to the x minus 1, which is indeed equal to the first derivative. So it satisfies the differential equation. What about the initial value? Well, y of 0, substitute in 0 into this, we get 2 e to the 0 minus 1 minus 0. Remember, you can always pause these videos. E to the 0 is 1, 2 by 1 is 2, 2 minus 1 is 1. So that all checks out. So the solution of this initial value problem is this function. A good question is, can there be multiple solutions? In general, basically no. Hence, calculate the percentage error in the numerical method estimate, presumably of y of 0.2. So we'll calculate the exact answer to so many significant figures. So we'll substitute in x equal to 0.2 into this. So we get y of 0.2 is equal to 2 times e to the 0.2 minus 1 minus 0.2. And we'll approximate this to, if we need more significant figures, we'll throw them in as we needed them, but 2e to the 0.2 minus 1 minus 0.2, I get, or sure, we'll throw in a shot at them, 2, 4, 2. Like if we got agreement between the approximation this to some, to like we have 6 significant figures, we'll throw in the 6 significant figures as well. But maybe they'd agree and we'd have to put in more significant figures here. But I think this is probably enough. Yeah, this is probably enough. So the error then in the calculation is the error, the difference between the exact and the approximation divided by always the exact, not the approximation. So the difference between these is in the 4th and 5th decimal places. So if I go on the calculator at that, I think I'm getting 3075. And the exact is to this many significant figures anyway, 6,242,80. Bang that into the calculator. Like you could do more significant figures in this calculation if you wanted, but I don't think there's much need. 24280. So I'm getting, like, as a number here, I'm getting 0.000, say 60. I will go with 4 significant figures. 3, 4, and the 4 is 47, so that rounds up. And then this is a percentage just multiplied by 100%. And so I think we get 0.0635%, which is very small. So we see this 3-term Taylor method being very good. I mean, it's what is it? 1/20th of 1%. It's very good. Okay. Okay, we'll keep going here. Yeah, we'll do another example. So use the 3-term Taylor method with a step size of 0.1 to estimate the value of y at x equals 0. We get this. So this is an example of a differential equation where the exact solution is horrible. So we won't be looking at there. So the 3-term Taylor method is the exact solution at k plus 1 is approximated by what we call yk plus 1, which is equal to the previous y value plus the step size times the previous slope. So notice I have k plus 1 and then k. So the k plus 1 means next, k means previous in that sense, times h squared over 2 times the previous second derivative. Okay, so that's what we'll be using. I think we'll be going back to this picture afterwards. The first problem is we don't know the second derivative. So the first derivative here is x squared plus y of x squared. So we're looking for the second derivative. It's the derivative of the first derivative. And the first derivative is given in the differential equation as x squared plus y of x squared. And what I'm recommending is you write the y as y of x. That's what I was banging on about earlier on. So this is equal to, it's a sum you can differentiate term by term. So derivative of x squared is 2x. And then you need a chain rule for y of x all squared. So the outside function is x squared, derivative of x squared is 2x. Chain rule says evaluate at the inside. Now you only have to write the y of x once. The inside is y times the derivative of what's inside, and the derivative of y of x is dy dx. And we know that dy dx from the differential equation is actually x squared plus y squared. So you get 2x plus 2y times x squared plus y squared. So the first derivative is x squared plus y squared, and this thing is the second derivative. We probably want a little table here to keep us going. So it's also x equals 0, y equals 1. That's not always that. It seems to be kind of the case here though. So where have we put our table? We'll chuck it down here. X, y, so 0, y is equal to 1. And then just double check that. Have we got? Yeah, x equal to 0, y equal to 1. X equal to 0, y equal to 1. And our step size, sorry about going back and forth, is h equal to 0.1. So we're going to 0.1, and I think the question is asking us to go to 0.2. Okay, so off we go. So the y value at 0.1 is approximated by what we call y1 here, which is equal to the previous y value. The previous y value is 1, plus the step size is 0.1 times the previous slope. The slope is, we saw this in the question, was x squared plus y squared for this differential equation. So it must be x squared plus y squared with the previous values of x and y, 0 squared plus 1 squared, plus h squared over 2, so that's 0.1 squared over 2 times previous second derivative. Now look at the second derivative. It's 2x. What's the previous x? 0. Plus 2y. What's the previous y? 1. Times x squared plus y squared at the previous point is 0 squared plus 1 squared. So what I'm doing here is I'm putting in the x and y, 0 and 1, into the first derivative and into the second derivative. I'll hardly get space here for the significant figures, but we'll give it a bash. So going into the calculator, I'm supposed to just pause for that. So if I carefully go into the calculator, I get 1.11, a bit of a fluke, but there we go. Okay, now we're going to, so that's 1.11. Now let's go again. What's going on at at x equal to 0.2? So that's approximately what we call y2, which is the previous y value, which is 1.11, plus the step size, which is 0.1, times the previous slope. Now for us, the slope is x squared plus y squared, and at the previous point, the x is 0.1, so we're looking at 0.1 squared, plus the previous y squared, which is 1.11 squared, plus step size squared over 2, and now I'm looking at the second derivative, so it's twice the previous x, which is twice 0.1, plus twice the previous y, which is twice 1.11, times x squared plus y squared. So I'm looking up here. So the previous x is 0.1 squared plus previous y 1.11 squared. And I will go off in and pause to go into the calculator for this. I think it's a bit of a fluke here, but it's kind of similar answers to the previous one. And we'll maybe explain why that might be the case. Actually, I don't think I can. We'll go with 6 significant figures here. 1.248, that's 4, and it does 997. So yeah, I'll just write what it is here. So 997 and then 3. Now if I'm rounding that to 6 significant figures, now look, the 9 will round up, the 7 round up the 9, and then that'll round up the next one, so you'll end up with actually 900. So 1.24900. Yeah, why has this got such similar solutions to the previous? Can we explain that? 1.242, 1.249. Suppose it's just when x and y here, so you're starting at the same place. I suppose when x and y are small, x squared plus y squared and x plus y are similar. That's the only reason I could look at it. It is a bit of a coincidence though. If we go back, if we go here, well, I suppose it's 1.25. It's a little bit different, but probably just a coincidence. A weird one though. Now this is like a picture, right? So you can see there's a slight, I think this is example 1, not example 2. You can see there's a bit of a second derivative here, right? That the slope is changing. Let's just say the slope is increasing. So Euler would struggle a bit with this. I don't think it would struggle greatly. I mean, you zoom in, it looks pretty much like a line, but there is a bit of a curve to it. But the three-term Taylor was really accurate. I mean, we saw the error was like tiny. So that's the three-term Taylor method. Now the problem with the three-term Taylor method is we've got this horrible differentiation. Look at this problem down below, exercise 1. You want to differentiate that yolk? Oh, nasty. So what we'll be looking to is, could we possibly improve Euler's method in a different way that makes the maths easier? That's what we'll be looking at next week.